So let's solve then this problem together using Newton's cooling law. So we have 4 power transistors, and each of them, like each of these transistors, is dissipating 15 watts. And they are mounted in a thin vertical aluminum plate, 22 centimeters by 22 centimeter inch in size. The heat generated by the transistors is to be dissipated by both surfaces of the plate to the surrounding air at 25 Celsius, which is blown over the plate by a fan. The entire plate can assume to be near isothermal, and the exposed surface area of the transistor can be taken to be equal to its base area. If the average convection heat transfer coefficient, or the H value that we need to solve Newton's cooling law, is 25, determine the temperature of the aluminum plate. And it says disregard the radiation effect, so just convection. So I want that we solve this problem in 2 ways. First, considering, like the problem says, that they dissipated by both surfaces, and that is dissipated by one surface only. So you can see the difference, okay? So please start working on that. I have here the solution. I will go just to here, up to here. So we have a heat transfer rate of 15 per transistor. We have the length of the plate is 22 times 22. We have the temperature of the surroundings being 25 Celsius, the convective heat transfer coefficient being 25 watts meter square Celsius, and we want to know the surface of the temperature. So we have 4 transistors, each dissipates 15, so 15 times 4, right? It says that we consider the whole transistor to be covering the whole area of the plate, right? So despite you can see the transistor have this kind of very distinctive structure, right? Or geometry, we are considering that it's the whole base, okay? We are not considering these as small features of the geometry. So the whole base, for simplicity. Then the surface area is going to be 0.22 times 0.22 for one side if the heat is only dissipated by one side, this side, right? If it is by 2 sides, is 22 times 0.22 meters times 2. That will give us the area of 0.096. I want that you calculate both. If it is dissipated the heat only by one side, and if it is dissipated by 2 sides. So this is how it looks like the equation, right? We just take TS, the T surface, out of Newton's cooling law, right? TS or T surface equals T surroundings plus heat transfer rate divided by convective heat transfer coefficient multiplied by the surface area. The surface area is the number that is going to change. If we are losing heat by only one side, we are going to use this value, 0.0484 meters square. If we are losing heat by 2 sides, we are going to replace the surface area value by 0.0968. That will give us different surface temperatures, right? And we expect a lower temperature when we are losing heat by both sides, right? So I will give you my numbers then. For one side surface, I got 74.6 Celsius, and for both sides, 49.79. Everyone got the same or similar if you use different decimals? Yep. So as you can see, Newton's cooling law and Fourier equation are 2 equations that you need to have in your note sheet for the exam, okay? Let's review pretty fast the third type of heat transfer. And again, we are going to revise each of them in detail in the course. Now is just to give you a brief overview. And the third type of heat transfer mode is radiation. And radiation is the energy emitted by matter in the form of electromagnetic waves or photons as a result of changes in the electronic configurations of the atoms or the molecules. In heat transfer, we are interested in thermal radiation. That is the radiation emitted by a body because of its high temperature. Okay, that's the type of radiation that we are going to be interested in this course, thermal radiation. Important note, energy transfer by radiation is fasted at the speed of light and it suffers no attenuation in vacuum. I'm sure you already know that. And as I already mentioned, radiation heat transfer occurs through electromagnetic waves. And here we just have a plot of the radiation intensity for several common wavelengths. And important to remark that all matter emits energy in the form of electromagnetic radiation in the proportion to absolute temperature to the fourth. And that is very important in radiation, actually. When we deal with equations related to radiation, we need to use absolute temperature, okay? So you need to change your temperature either on Rankine or Kelvin because the equations were developed to be used for absolute temperatures. Okay, so very important. When using equations for radiation, use absolute temperature. That's a common mistake I have seen in exams and homeworks. Okay, radiation, absolute temperature. So how we describe radiation? So for conduction, we have Fourier. For convection, we have Newton's cooling law. For radiation, we use Stefan Boltzmann law. However, this equation that I'm showing in this slide, that is heat transfer emitted equals Stefan Boltzmann constant times the area times temperature absolute to the fourth, applies only to black bodies. What is a black body? A black body is an idealization, okay? So this equation is only applied for the ideal case of a black body. What is a black body? Black body radiation represents the maximum amount of radiation that can be emitted from a surface at a maximum specified temperature. So it's the max amount of radiation a body can emit at a certain temperature. That's the idealization of a black body. And to evaluate the rate of radiation like a black body, we use this form of the Stefan Boltzmann law. That is the Stefan Boltzmann constant, and I put here the values of that constant for you in international system and in English system, times the area, times the temperature, very important, temperature in absolute scale, either Kelvin or Rankine to the fourth. For winter, we have the temperature of the surroundings in winter being 10. The temperature surroundings in summer, 25. The surface temperature or the person temperature, 30 Celsius. And the person has a surface area of 1.4 meters square. So Q radiation in winter is going to be epsilon, emissivity 0.95, times the Stefan Boltzmann constant, in this case in international system, times the surface area of the person, times the difference of temperature in absolute scale to the fourth. So 30, that is the person's temperature, plus 273 to the fourth, minus 10, that is the surroundings winter temperature, plus 273 to the fourth, give us 152 watts. Simultaneous heat transfer mechanism. So I told you that sometimes it is not only conduction that is important, not only convection, we have mixed. And you need to decide, that's another thing, you need to do these kind of educated selections, like which one is very important in this process. If it is conduction and convection that are dominating, if it is conduction and radiation, or it is the three of them. So in this problem, we are going to consider radiation and convection important. So we have, again, a person standing in a room at 23 Celsius, and we are going to determine the total rate of heat transfer from this person if the exposed surface area and the skin temperature of the person are 1.7 meters square and 32 Celsius, respectively. And the H value, the convective heat transfer coefficient that we use in Newton's cooling law is 5 watt meter squared Celsius. Take the emissivity of the skin and the clothes to be 0.9. That is our epsilon for radiation, right? And assume the temperature of the inner surfaces of the room to be the same as the air temperature. So we need to first get what? Convection, and then get radiation, and then add those 2 watts or heat transfer rates. Because the problem says consider both of them are important. So you have handy your Newton's cooling law, right? We used it in previous examples. We used in the previous example Stefan Boltzmann. So we just need to apply those 2. Is that you just identify the 3 main equations and that you use them in pretty simple examples. In all my courses, we keep building from simple to complex, okay? So maybe at this point might be kind of easy for you, but it's fine. We will be complicating stuff. So radiation, I got 84.8 watts. Convection, I got 76.5. And total, it will be 161.3 watts. And we already talked about this in conduction. It is Fourier law, what it is helping us to calculate heat transfer rate, right? And typically in any textbook, in your textbook, any other that you check, any transport phenomena book, you will find this slab to develop the Fourier's law. And as I already explained last class, they put typically this minus, right? Because we have a negative slope here. Since the heat is conducted in the direction of decreasing temperature, as you can see in the slab, then the temperature gradient is negative when the heat transfer is conducted in the positive direction. And that's why we add this negative to ensure a positive heat transfer rate. However, in order to forget about all that complication, just remove that minus sign and just don't forget to always do hot minus cold, right? That's it. So this is the equation. We will be using hot minus cold here at all times. So if we arrange our Fourier law similar to Ohm's law, we can see a lot of resemblance, right? In Fourier's law is the delta T, which is the driving force, whereas in Ohm's law is the delta of voltage that results in an electrical current. So if we rearrange them together, we can see if they look pretty similar, right? And the denominator in Ohm's law is the electrical resistance. So we can name here this delta X over Ka, or the thickness divided by thermal conductivity area, as the thermal resistance. So we can rename it like that. And this is the thermal resistance and electrical analogy that help us to solve problems when we have different walls of different materials all together. And we do this a lot in engineering, right? Like, for example, even in houses, we need to add insulation. We need to add layers, right? Layers to the walls, right? To impede the heat transfer, right? That's the main use of insulation. Or in pipes, we also surround our pipes, right, by another layer of insulation, right, in order to impede the heat transfer rate, right? So this kind of analogy is very important in heat transfer, very, very important, and it helps us to solve problems when we are dealing with all these layers, okay? Layers of walls or cylinders. So this analogy is pretty important, and it comes from this simple view of rearranging the Fourier law similar to Ohm's law, and recognizing that this term is what we are going to call thermal resistance, because it's similar to the electrical resistance in Ohm's law, right? Just because of that. So then here I'm just showing the difference between an electrical resistor and a thermal resistor. One for electrical conduction, the other for heat conduction. And that we are going to define our thermal resistance then as delta X, the thickness of the wall, divided by K, thermal conductivity, and the area. So if we have two or more materials joined together, forming a multi-layer, the total thermal resistance is the sum of each resistance for each layer. So you have to add all the resistances depending on the number of layers you have, okay? And that is much easier to see with an example. So let me show you this composite wall. So this wall is made out of 3 different materials, right? This is one material, this is another material, this is a third material or a third wall, right? And it's surrounded by air, water, any fluid, right? That's why we have these H values in here, because they denote a fluid is there, okay? What if we want to calculate the heat transfer rate through this wall? Well, we have to make the difference of the surrounding temperatures from the two walls, because we want to calculate the heat transfer through the whole composite wall, the whole composite wall. So it will be T surroundings 1 minus T surroundings 2 divided by R total. R total in this case is the total resistance between the two temperatures, between this T surroundings 1 and this T surroundings 2. So how many resistances we have? Let's count. Our total is going to be, we have one convective resistance, right? Why? Because we have a fluid in contact with our first wall, right? That's our first convective resistance. Then we have our first conductive resistance, because it's the resistance due to the presence of this wall. Then a second conductive resistance, because we have a second wall. Then a third conductive resistance, because we have a third wall. And finally, a second convective resistance, because we have a solid and a fluid interface. How many resistances in total? 1, 2, 3, 4, 5. 3 conductive, because we have 3 walls, and 2 convectives, because we have 2 interfaces, solid, fluid. And that value is going to be in the denominator, right? And if we divide the delta T, our gradient of temperature through the whole wall, by the total resistance, we have heat transfer rate through the wall. Yes. So if I want to calculate the temperature through the whole wall, and we are going to stop here, we calculate each resistance. So I have here the calculation for each resistance. Please go through this at home. And you have the formulas here. You have the data for this wall in here, okay? So you have everything to calculate all the resistances. You add the total resistances. The difference of temperature divided by the total resistance give us the heat transfer rate through this composite wall.